next in the series is first topic is lead lag compensator design, which is somewhat extension of PID control design. So, let us see how it operates actually. Last class we saw that PID control design essentially has 3 loops. One is proportional feedback, one is integral feedback and derivative feedback. This is how it operates: proportional feedback, integral feedback and derivative feedback. However, the problem in PID design is requirement of pure integrators and pure differentiators, right. I mean, if you see these 2 loops, what you need to realize is pure integrator and pure differentiators, which are normally difficult to realize. And in addition to that, there is also a small danger that this pure integrator pole, which is supposed to be there exactly at the origin, that means the pole is somewhat here in the origin, by realization difficulty, like that inaccuracy or whatever, there is a danger that this pole may slightly be realized in the right hand side actually, then the system becomes unstable and all that actually. It is not a good idea to do that kind of a thing. So, the question arises is can we avoid this difficulty? Okay. All right, just a second. Okay. Now, the question is can this difficulty of the PID control design be overcome, but we do not want to compromise too much on the basic design philosophy. We want to retain the basic design philosophy, but at the same time, okay, we want to avoid these difficulties of the PID control design. So, can we do that? The answer turns out to be yes, and that is how we will do that through something called lead lag compensator design. Sometimes it is also called as large lag compensator design, it does not matter, the concept is same anyway. So, let us understand the ideal integral compensation, and that is what typically we use for improving the steady state error performance actually. So, in addition essentially this does not have a D loop, but it still has I loop, that means it is a PI controller. So, the realization difficulties have been something like this. How do you do this? This is the original plant. Okay. The problem is like this. This is the original plant. This is the root locus for the plant. Okay. And then we have a point A, which is the desired pole location, because this particular point A gives us the required transient performance. Transient performance, and there is no issue actually. Okay. However, the steady state error is not good. So, we want to improve that through this integral compensation. Okay. But the problem here is once you have the integral compensation in place, then the root locus is no more like that. Okay. The root locus is somewhat different. So, obviously, the point A, which is your desired pole location, is no more on the root locus. That means, simple gain adjustment will not do the job actually. Okay. So, now the question is how do we overcome that? Obviously, one idea is just put a 0 along with that pole actually, okay, very close to each other. Okay, put a 0, okay, close to the pole. Okay. Once you do that, if you see the angle contribution, essentially it again becomes odd multiple of 180 degree. Okay. So, essentially the root locus passes through that. Okay. Originally it was 180 degree, odd multiple of 180 degree. The moment you add one pole, the extra angle contribution made it unequal. However, you do not want the pole to go somewhere else, you just want it here itself, because that gives you the required transient performance already. So, by adding a 0 close to each other, then these 2 angles are roughly same. Okay. So, that means you are not compromising on the transient performance, yet improving the steady state performance. So, what you look at it, you need a compensator not like that, but somewhat like that. And what is it? This particular compensator can be visualized something like this. If you expand it, turns out to be a pure integral, pure PI controller. Okay. But you want to avoid that. So, what do you do? The whole idea is, can we shift this pole 0 pair, whatever pole 0 pair it appear to be, okay, can we shift it slightly left, okay, slightly left. Okay. So, this is almost like on the origin, but it is not really on the origin actually. Will it do the job actually? That is the question. Now, it turns out that if you analyze this error constant, for example, let us say you talk velocity error constant, then originally it was something like that without any, only with the proportional loop, not I loop. However, with the compensator, remember this no more a PI controller, it is a lag compensator. Okay, the lag term probably comes because the 0 is lagging the pole in that sense actually. The 0 is numerator, probably that gets a preference maybe. Okay, so because of this compensator, now this KV1, the new error constant turns out to be that one. Okay, because the extra 0 will come here, extra pole will come here, and as long as that ZC is greater than PC, that means this error constant will be greater than the previous error constant. And also remember that compared to the if you have a type 1 system, then the steady state error is inversely proportional to that actually. Okay, so I mean if this error constant becomes larger than the previous one, obviously the steady state error becomes lesser. Okay. So, in that sense we are still able to do the job without compromising on the PID control philosophy much. Now, the question is how do you do that? How do you make it sufficiently large compared to that actually? So, first thing is you have to put this pole 0 pair close to each other, because that will not add to any angle contribution much actually. Okay. Second thing is to make this substantially larger, you make this ratio substantially greater than 1. Okay. So, how can that happen? This ratio substantially greater than 1. Because I mean, you can do that by putting the pole 0 location very close to origin actually. Okay. Because if this is let us say 0.01, this is still 0.1 let us say, then you have 0.1 divided by 0.01, which is like 10 times actually. Okay. So, you can still improve this ratio by 10 times by putting close to origin actually. So, that is the philosophy of lag compensator essentially. So, by putting it very close to origin, it is like a PID controller actually. Okay. So, that is what it is. So, this is the overview of originally this pole was here, and then by using a lag compensator, we will be able to roughly retain the same root locus, yet improving the steady state error actually. Okay, that is the whole idea here. Okay. Now, coming to the lead compensator, the objective is to improve the transient performance instead of the steady state error, but I mean ideally we can do that using a pure PD realization, but again we want to avoid the pure PD realization, because we want to avoid the differentiation loop. The advantages, primarily it avoids realization difficulties, that is it avoids requirement of additional power supplies in electrical circuits for example. That means, pure differentiators can be realized through some devices which requires additional power supplies, that can be avoided. You can realize this through passive devices, and then more important, it actually reduces the noise amplification due to differentiation, because it is not a pure differentiation. We know that pure differentiation has a noise amplification property. So, that one gets reduced actually. The drawback turns out to be that pure 0 in the PD controller tends to reduce the number of branches of root locus that travel to the right half plane. So, having a pure 0 I mean in the PD controller changes the root locus behavior. The root locus does not go to the right half plane actually. Okay. So, that gives you additional flexibility of improving your gains and all that, because the root locus does not go to right half plane anyway. However, this one I mean using this lead compensator you are not capable of doing that, that is the only drawback actually. Okay. Now, let us understand the philosophy. So, what we are doing here is the desired pole location was somewhere else, we want to make it here actually somewhere in the desired root location, I mean desired pole location actually. And remember, because this is not part of the original system, that means the original root locus does not pass through it. So, hence we cannot just tune the gains, so that select just don't we are not able to tune the gains, so that we will get the desired performance actually. Okay. So, how do you do that then? So, primarily there is a problem, because this angle what you really want, remember root locus is primarily coming from angle condition, that all the angle contributions zeros minus poles should be odd multiple of 180 degree. Okay. So, if I add a pole 0 pair again here something like this, then what happens actually? Okay. There is additional angle contribution through this difference theta 2 minus theta 1. Okay. That is the additional angle difference, which will this angle, if you see this side, this theta 2 minus theta 1 is that angle actually. So, this additional angle will make sure that the root locus passes through that particular point that you are interested in, and hence you know this what is the gain corresponding to that, and you will be able to select that gain actually. Okay. So, that is the whole idea. Now, what it tells us, as long as this angle is same, okay, this angle is maintained, the pole 0 locations can be anywhere actually. Okay. That means I can put this pair anywhere on the real axis, okay, wherever I want, as long as they contribute this angle difference out there. Okay. So, that essentially gives us a flexibility of putting in a number of locations, and different selections results in obviously different other performance behavior, and essentially different gain values to reach the desired point, because if you select different locations, you really need to select different gains actually. So, that because I mean corresponding to these pole 0 location there will be a different I mean there will be a particular gain, corresponding to this pair there will be another gain, things like that actually. Okay. And also remember that as far as static error constants, that means the steady state error behavior is concerned, okay, that depends on these pole locations actually, pole 0 pair location. So, that is in that sense there is a requirement of tuning these locations also basically. Okay. So, that is the philosophy of lead compensation. Now, what is lead lag compensator design? Essentially is a combination of both the two, I mean both lead and lag compensators. So, what do you do? First evaluate the performance of the uncompensated system, that is true for any control design by the way, okay, just to see how the system performs, and if there is a necessity then only do something, otherwise if the system is already good then do not try to unnecessarily design a controller actually. Now, if necessary then design a lead compensator first and try to improve the transient response actually. Okay. Next you design a lag compensator to improve the steady state error over that transient performance. Okay. Then you do the you have to do the simulations to make sure that all requirements have been met. Remember, many of the times we are forced to do some sort of a second order approximation of the actual plant, which is not true. So, hence there is a necessity to simulate the system actually. Okay. The dominant pole and other things will come as approximate second order plant and all that, that is not true. So, after you tune up all these with respect to that approximate second order plant, go back to the main plant and try to simulate and make sure that all things have been met actually. If not, redesign the compensator, that means retune the compensator gains and probably pole 0 locations as well actually. Okay. So, if the simulation performance is not satisfactory, do that, if it is satisfactory you are done actually. So, that is the procedure for lead lag compensator design. So, that essentially completes this particular thing. And next big topic in classical control is something called frequency response analysis. It is a parallel development and probably the earlier development as well. Okay. Earlier people, when they started looking at feedback control systems, this is the one that came to the mind first actually, and then root locus came much later. I mean if I am correct, then this frequency response analysis somewhat in between first and second world war, and the root locus and modern control and all the things happened after second world war actually. So, but it is a very important concept. There are many things that can be done in a very intuitive manner following this frequency response analysis. So, let us see the concept. So, here we will be primarily interested in sinusoidal input, no more constant and ramp input and things like that actually, no more step input, ramp input like that. Let us see what happens if you give something like a sinusoidal input. Okay. This is the input that I am giving, and as here I am considering a spring mass damper system, which is also equivalent to RLC circuit actually in electrical system. Most of the mechanical systems including aerospace engineering are typically spring mass damper systems anyway. Okay. So, what I am looking at? I am looking at a sinusoidal signal, and it turns out if the system is a linear system, then the output will also be sinusoid. Okay. And it interestingly turns out this sinusoid, output sinusoid will also contain the same frequency as the input, frequency part remains same. So, what is different then? The difference is in the magnitude and phase actually, there is a magnitude difference of the output. Okay, and there is a phase lag of the output as well actually, there is a phase difference actually. Okay. So, if you really consider however, this magnitude and phase difference is a function of this frequency. Suppose this frequency is different, then then the magnitude and phase will also be different actually. Okay. So, I can interpret this input signal as some sort of in a phasor form, what is called. Okay. So, it is a magnitude and phase angle. If I give that, then I will get another signal with a different magnitude and phase. Obviously, all these are functions of that particular frequency that this signal contains. Okay. Then I can interpret that this particular system that I am talking about also contains some sort of a phasor form response, I mean characteristics actually. So, that is the frequency response of the system actually. So, what I am looking at, if I am looking at the output signal, the steady state, remember we are talking about steady state output, not transient output here. Okay. Giving a signal and waiting until it I wait until it reaches to the steady state condition, then I am analyzing that particular signal actually. Okay. So, steady state output of the sinusoid, what I am looking at here is something like the frequency response of the system multiplied by the input sinusoid actually. Okay. And it will also turn out that this in this magnitude, if you do the proper analysis in time domain also, and details are there in Norman-Nice book as well. If you do that, it turns out that okay, this magnitude will multiply and the phase angles will sum up actually. Okay. So, what I am looking at, if I am looking at this particular magnitude of the system, okay, then this magnitude response is something by magnitude of the output divided by magnitude of the input, and the phase response is the phase difference between the two actually. So, together this m of omega and phi of omega, magnitude and phase, they contain the system property together, and these two pair is known as frequency response actually of the system. Okay. And I mean it is very clear that if I vary omega, then these two will also vary actually. So, what is little more detail, if I see that in Laplace domain, I am giving some sort of a combined sinusoid, a cosine and sin omega t together. I can interpret that as something like this. This is the magnitude and this is the phase angle actually. So, this is in the form of mi cos of omega t minus phi I, where mi and phi I are defined like that. And after appropriate analysis, what you are looking at is the time domain analysis, time domain response for this C of s, that means C of t, and that you are essentially interested in steady state response actually. Okay. And if your system is stabilizing, remember that this steady state response will approach to the reference signal actually. Okay. So, all these analysis details are there in the Norman-Nice book actually, you can see the details. And then what I am looking at, this the steady state time domain response is given by something like that very clearly. Okay. It comes through that analysis actually. You can take a Laplace transform and then invert the Laplace transform, do partial fraction, all sort of things actually, that is there, details are there. So, interestingly it turns out this mg and what you are looking at, this mg and phi g, these two angles, these two conditions, these two variables are clearly given by these actually. Okay. So, mg is given as magnitude of this g j omega and phi g is given as angle of g j omega. Okay. So, because of that the frequency response characteristics of this particular system G s is nothing but g of j omega. If I simply represent that in a complex plane probably, in a phasor form, then I can simply contain this magnitude and phase together and talk okay, g of j omega is nothing but the frequency response of this particular thing. It contains both magnitude thing and as well as phase thing actually. Okay. So, what is frequency response formally? Now, we know that this closed loop transfer function is Cs by Rs. Okay. So, if I substitute S equal to j omega, then T of j omega contains a magnitude and phase, and the magnitude and phase together are called the frequency response. Is we have been telling that over 2-3 slides now. This is one and the same thing actually. Okay. Now, to analyze this frequency response formally, there are many nice tools available actually, and very intuitive thing that comes to mind is Bode plot, followed by Nyquist plot, then Nichols chart, constant eminent circle, things like that actually. We will not talk too much details, but essentially it probably starts with Nyquist plot and then it leads to Bode plot. However, for our better understanding, we will study Bode plot first and then go to Nyquist plot. Nichols chart probably we will skip actually, that is also easy to follow, you can see the book also. So, let us see first what is Bode plot analysis. Okay. So, you have a transfer function something of this form, okay, and then what you are interested in? We are interested in studying the g of j omega, its magnitude and its phase angle actually, that is all we are interested in studying. Okay. So, what I am looking for is the magnitude of g j omega, but we are interested in studying this particular magnitude of g j omega for a wide range of frequency actually, for a very small frequency to a very large number. So, a better way of studying that is with respect to logarithmic scale. Okay. So, what I am looking at is something called decibel with unit. So, I am looking at 20 log of magnitude g j omega, that is the magnitude in dB, that is in decibel actually. Okay. versus frequency, and frequency also is a very wide spectrum, a very wide range. So, I will also interpret that in terms of log omega. Okay. So, what I am doing actually as far as magnitude is concerned, I am expanding this 20 log of magnitude e j omega, which will turn out to be like this by using simple logarithmic expressions, and then the angle part will turn out to be angles contributed from the zeros minus angles contributed from the poles actually, okay, all evaluated at s equal to j omega. Okay. All these things will be evaluated at s equal to j omega. Okay. So, what is the beauty? Beauty is both leads to addition and subtraction only, there is no multiplication after that. So, this addition subtraction in the magnitude, by taking logarithm, we have converted it to a multiplication, I mean converted from multiplication and division to addition and subtraction, and by nature this phase is anyway given in terms of addition and subtraction. So, as algebra becomes very simple, and it is possible to plot by hand actually the frequency response characteristics. That is what I told, the Bode diagram has several advantages, very intuitive things of analyze, very intuitive tools to analyze. As I told, algebra is through addition and subtraction, okay, and that too mostly through simple straight line asymptotic approximation. We are not interested in exact curvature of the response and things like that. We will be able to do this very quick analysis using what are called asymptotic approximations of the response actually. And this the second point is this low frequency response contains sufficient information about the physical characteristics of most of the practical systems. The high frequency vibration, for example, we are not that much interested, we will consider that as a noise actually, very high frequency vibration. What you are interested in vibration response is something, if you just give some sort of a dip to the system or some sort of excitation to the system, then how it really vibrates in a low frequency mode, that contains the system characteristics that we are interested in primarily actually. Okay. So, low frequency response is what your control system is able to do, and that is what is our primary intention actually. However, this Bode plots are for all frequency range. So, Bode plots will be able to plot it for a wide variety of frequency actually. Okay. Then as a byproduct, what it turns out is this experimental determination of transfer function is also possible through Bode plot analysis using this corner frequency and all that. Suppose you do not know the transfer function in the beginning, but if you go back to this, so and these values you want to find out actually, this location of zeros and location of poles, and it will essentially turn out that these are also locations of this corner frequencies in the Bode plot. We will see that in a while actually. Okay. So, if you roughly see the Bode plot and then find out the corner frequencies and roughly the nature of the plot actually, then you will be able to predict these values in a good way. Okay. So, that is what system identification is about. Through Bode plot you will be able to do that actually. Okay. That is an additional byproduct, but we are not going to discuss too much on that actually here. Yeah. So, what is Bode diagram? I mean it is essentially Bode diagrams is a frequency response of magnitude and phase angle together, and then we are interested in plotting that in a logarithmic scale, and then it turns out that there are two notions for that. One is octave and the second is decade actually. Okay. So, the frequency band from like some omega 1 to 2 omega 1, essentially if you double the frequency, whatever happens, that is in a logarithmic scale, that is called octave, and if you multiply frequency to 10 times, okay, whatever happens in the logarithmic scale, it turns out that is known as decade actually. Okay. And something that frequently appears in our transfer functions, if you see this transfer function, is actually all written in first order form, but that may appear to be partly second order form also. Okay. So, that means instead of this s plus p2, this particular term I can interpret that as some sort of a second order polynomial also basically, like that way. So, it makes sense to study some of the standard things that appear. Okay. That is this suppose you have an integral term, so either you can have a pure gain is no s to the power 0, or you have an integral or derivative term which is s to the power either plus 1 or minus 1 depending on whether it is a 0 or it is a pole actually, or you have some term like 1 plus s either in the numerator or in the denominator, or you have this 1 plus 2 zeta omega n plus omega n square sort of thing actually. All these are written in normalized form by the way, that is a standard practice that is done in Bode plot analysis. Once you normalize the entire quantity, suppose I take normalize, I divide it by g1, I mean z1 here, z2 here, p1 here, p2 here, then all that I am doing is multiplying this gain by some other constant. So, it turns out to be an overall gain factor actually. Okay. So, that helps me in drawing the Bode plot in a good way actually. So, that is the reason for getting normalization and all that. Alright. So, details Bode diagram for constant gain and then some varying the gain k, what happens and all that. So, all sort of things are possible here. So, what is happening for constant gain k? If the gain is constant, then the log magnitude curve is also a constant line, right. If you take a logarithmic of a constant value number, it also turns out to be a constant. Okay. So, the constant line turns out to be 20 log k in dV, that is it actually, and because it is a scalar number sitting in the numerator that too. So, the phase angle is 0 actually. Okay. So, whatever number is that, I will interpret that phase angle is 0. And then for what I am doing is for varying the gain k, okay, if I really have gain variation, what happens here? If I gain initially was k1 and later is k2, then with respect to k1, then k1 and k2, the Bode plot will essentially shift up and down. Okay. Because there is if I multiply by some quantity, let us say the original gain, then multiplication turns out to be addition in logarithmic scale. So, essentially I will add it some constant value throughout, or I will subtract a constant value throughout actually. So, that is like it will take the Bode plot up or below as far as the magnitude plot is concerned. Phase angle is 0 anyway actually. Okay. So, similar analysis you can do, and especially if you have a 1 plus s term, okay, 1 plus omega by a in a normalized manner, then essentially it can be approximated by 2 straight line sort of thing. So, let us study that part of it actually. So, either you have g of s is s plus a. So, what you have is g of j omega is j omega plus a actually. Okay. So, at low frequency what happens, if omega is very less than a, compared to a omega is very less, then I can approximate this quantity as nothing but simple a, right. J omega is almost 0 actually, okay, that is gone. So, I am left out with g of j omega is a. So, magnitude and phase of that particular time when omega is very less, low frequency, turns out to be this number, and the phase angle is 0 actually. At high frequency, okay, what happens? The reverse happens. Okay, this the approximation sense, I can forget the a component because omega is very high compared to a. So, g of j omega is nothing but simple j omega actually, and if you see that phase part of it, phase part of it is 90 and the magnitude part turns out to be like that, which is actually a straight line. This particular thing, if you see 20 log omega is a straight line with respect to log omega in the x axis. You put that if you put this in y axis and then log omega in the x axis, then it is nothing but some y equal to like 20 times x basically, that is a straight line. Okay. So, what happens? Then when does this change actually? This first it is a constant, then this is a straight line approximation. When does the change happens? The change happens through something called corner frequency, and that is where if you normalize this and interpret it that way, when this when do you consider that this is high or this is low, depending on whether this is less than 1 or greater than 1 actually. If it is less than 1, I will dump it as something like omega is very less than a. If it is greater than greater than 1, then I will consider that a second case actually. Okay. So, the corner frequency happens to be just magnitude a. So, this is what it is actually. So, the lower side of the frequency, that is just a constant line, and at a this is a straight line starting from that actually. So, these are like asymptotic approximation actually. So, in this logarithmic scale that we are looking at, log omega in the x axis and 20 log m in the y axis, this turns out to be like that actually, this for this particular s plus a. And phase angle, remember that phase angle is something like starts with 0 goes to 90, okay, and this starting and going to 90 should happen around that corner frequency. Corner frequency is a, and remember the Bode plot needs to be plotted on the same scale next to each other, just one below the other actually on the same x axis scale. Okay. So, if you see this a, okay, around that this frequency change happen, this phase angle change happens to be 90 degree. So, I will consider that, okay, if I go 10 times below this particular a, okay, this is all kind of thumb rules actually. If I go 10 times below that, then I consider from there onwards everything is negligible. So, that means that is a straight line, and if I come 10 times higher than that, from there onwards everything is valid in a high frequency range sort of thing. Remember this high frequency range is 90 degree, low frequency range is 0 degree. Okay. So, anything that is 10 times lesser I will consider that as 0 degree, anything that is 10 times higher I will consider that as 90 degree, in between there is a straight line approximation actually. Okay, this it varies through that actually. So, that is the Bode plot for magnitude and that is the Bode plot for phase actually. Now, similar analysis we can do for various things, either for first what we did previous slide is S plus A, we can also do that for S, we can do that for 1 over S, we can do that for 1 over S plus A also. And these are very easy to do rather, okay, because these are simply straight line approximations anyway. So, if you consider S, this just starts from beginning to end, okay, 1 over S the reverse way. Okay. Now, we studied this one S plus A, then if it is 1 over S, it just happens to be in the other direction. We had this kind of characteristics, remember that this type of characteristics. If we have 1 plus A, sorry 1 by S plus A, then it will turn out to be just the reverse way. Okay, then the slope will be negative. Okay, so that will start with the corner frequency A. Okay, and this all these are normalized plots. Remember that frequency divided by A sort of thing actually. Okay, so it will all start with that corner frequency, and instead of going up, it will go down. And here also instead of going from 0 to 90, it will go 0 to minus 90 actually. Okay, so these terms are rather easy to do actually. Now, what about a general transfer function like this? Okay, so then what happens is a nice property that we studied here comes to picture. Okay, these are all summations and additions and subtractions. So, what we will interpret is individually we will plot the magnitude and phase angles, then we will simply take the summation addition or subtraction sense actually. Okay, so that is what is happening here for a generic way. I will just do that for constant gain, then S plus 3, then S plus 1 and S plus 2 individually. Okay. And then I will just sum it up actually. Okay, that is what is happening in the first subplot individually. For example, if you see this 3 by 2 S, that is the gain, this one. Remember, this is a normalized, so you have to divide it everywhere, divide by 3 and then divide it by 1, divided by 2 like that actually. So, 3 comes out from here and 2 comes out from here. So, that is 3 by 2 K will appear here actually. Okay. Remember that okay, if I just do that a little bit. So, this is actually something like K 3 S plus S by 3, okay, plus 1 divided by S into S plus 1 into, okay, I will take 2 common, 2 into S by 2 plus 1. Okay. This 2 and 3, that is so that is what this K into 3 and this 2 will lead to this 3 by 2. Okay, that is what here actually. Okay. So, okay, all right. All right. So, this is how what is happening. So, 3 by 2 S is just like 1 by S sort of thing. So, it will start with and then go down in a straight line manner. Okay. Then if it is coming to like S plus 3 for example, this is the term. Okay. So, the corner frequency happens to be 3 and 3 is this is, remember, this is a logarithmic scale, that means this is 1, this is 2, this is 3. By the time you come here you are 10 actually. Okay. So, this is that way. So, at value 3 this starts going up actually. Okay. Right, and then a similar thing at if you see the pole should go down and then S plus 2 is somewhere here. Okay. Corner frequency is 2 actually. So, at 2 it will start going down actually, like that you plot everywhere, and then once you are done with all the terms you simply add it up actually. So, you just start adding up, then wherever there is a first corner frequency there will be some change there. Okay. Then it will go to the next corner frequency with a different slope, because slopes will get added actually here, plus minus sense actually. Then it will go to the next corner frequency and like that actually. So, that is the phase angle, sorry, that is the magnitude part, and similar thing we can also do for the phase angle part actually. Phase angle part we will draw individually first and then sum it up actually. So, it is just possible even to take a logarithmic graph sheet and then do our take a scale and pencil and then try to do this actually. I mean, it is just possible to do that, and that was a very beautiful part of it when computers were not available actually. Nowadays, of course, you can just plug it this particular transfer function and generate the whatever you want, root locus, Nyquist plot, Bode plot, everything in a computer, probably using standard softwares like MATLAB. All these things are easy. However, if you still want to do it by hand, it is possible to draw these diagrams using a graph sheet actually. Now, just remember that what we did here, these are all asymptotic approximations. That means, we are just interpreting at one corner frequency, everything below everything below that is one range, one sort of behavior, everything after that is one sort of behavior. Okay. So, that is not true, actually it is a fairly continuous manner, and if you see that the actual response actually turns out to be something like that. If you really plot these transfer functions and all, it is not going to be 0 0 0 up to 1 and then suddenly start I mean there is a slope there actually. Okay. But that slope is also 20 dB per decade actually. So, that is that is also there actually. Okay. That slope is 20 log A, right. So, this 20 log A will give you this 20 dB per decade sort of thing actually. Okay. If you have a second order transformation, the transfer function becomes 40 dB, just double, because omega square will take you 2 times of that actually. We will see that in a while. So, this is the difference actually. So, what you are doing in a graph sheet is this two asymptotic thing, but whatever is the reality is something like that. Remember, the maximum difference happens somewhere around the corner frequency, and this difference happens to be of the exactly 3 dB rather. Okay. This difference of this what you are interpreting as 0, but actually there is a 3 dB magnitude here. Okay. So, that is how it is happening, and the phase angle also happens to be something similar actually. Okay. And like now coming to the second order sort of behavior, you have a transfer function something like this either in the numerator or in the denominator. So, how does it happen? So, you again substitute j omega instead of s and then carry out the analysis. Now, it happens to be a function of this omega by omega n whole square, and that whole square will come out. So, that will be like 40 dB actually. Okay. So, if this ratio, remember these are all base 10 actually, all logarithmics are of base 10. So, if I have 10 here, okay, then that log 10 will become 1 sort of thing. So, this will be 40 dB per decade sort of thing. The slope that you are looking at is 40 dB per decade, that is how it happens actually. Okay. And the angle is also given something like that, magnitude is given, okay, something like this actually. Okay. We can still do the corner frequency sort of idea analysis and all that, and that is possible, but remember that these are not as neat as first order terms actually, these are now functions of zeta basically. Okay. So, you can still have some asymptotic behavior sort of thing, but remember, just remember that the departure from that approximation is not small, okay, and they can be significant depending on what value of zeta you have. For example, if you have very low damped system, that is zeta is 0.1, then you have a departure correction or something that requires actually around that frequency is quite high actually. Okay. And in phase angle also actually same thing happens. Okay. And it is very close to each other, like asymptotic behavior and other things are very close to each other around the operating zone. Remember, most of the second order systems either by nature or by design will require zeta to be 0.7. Okay. That has some certain beautiful characteristics actually. Now, if you see 0.7, 0.707 or 0.7 something like that, then this particular thing what you are looking at is very close to the asymptotes that we will talk actually. Okay. And same thing happens here also. Okay. And there are and further analysis what you will see at the end actually, why this 0.7 is a beautiful number for zeta actually. Yeah. Anyway, so this is what happens in the, if it happens in the denominator instead of in the numerator, what you have it actually becomes a mirror image actually. Instead of going up, again it will come down actually, and instead of that way varying this phase plot, it will vary this way actually now. Okay. So, that is what it is. Now, how do you do this? That particular example, let us say you have 2 first order terms and 1 second order term. So, first process is normalization. So, I will know, okay, below I mean the corner frequencies and all that actually. So, here I will take out 3, here I will take out 2, and here remember it is 5 square actually. So, I will divide to everywhere 25, okay, and then take it out. So, all these things become 3 by 2 into 25, that means 3 by 50 here, and numerator corner frequency is 3, this fellow is 2 and this fellow is 5 actually. Remember, this is what we discussed here, this omega by omega n, this plays a role actually. Okay. So, when at omega equal to omega n, okay, that is log 1 sort of thing, that is 0 actually. Okay. So, that is what we will look at it actually. Okay. So, this is something that we plot, okay, and then this individually will plot that, okay, and remember this is the second order part, okay, second order part compared to first order part, okay, will be higher slope actually. First order part will vary at 20 dB per decade, okay, but second order will vary sharply, I mean double the slope actually, minus 40 dB per decade sort of thing here. And then after you do this addition, subtraction, corrections, I mean the final asymptotic plot, then there will be a requirement of correction term also actually. So, these correction terms are also calculate, I mean roughly you can calculate that around the corner points, and you can put that. Some details are there in books like Norman Naish and Ogata and all that actually. Okay, you can see that. Similar thing you can do for the phase as well actually. Okay, phase plots you draw individually, then sum it up actually. Okay, so that is a summary about Bode plot analysis. Now, very quickly we will see Nyquist plot analysis also. So, and essentially as I told, Nyquist plot analysis happened probably before Bode plot. Bode plot happens to be quite easy to draw, analyze and all that, but a lot of nice things also happen in frequency response from Nyquist conditions actually. So, what is it? In this particular thing we are looking at simply the polar plot actually. Whatever this frequency response that you are talking, this m and phi we will simply plot it in a polar coordinate actually. Okay. So, this angle is something that you are interpreting as angle of j omega, and this magnitude what you are looking at is something like magnitude of this particular vector, okay, for that particular omega is nothing but the magnitude of this particular transfer function. Actually, this t is also g, what is depicted here you can interpret t as g actually here. Okay. And now, this particular thing is actually a quite intuitive thing, is that means there are if you have type 1 system, type 0 system or type 2 system, there is a very neat property that you can see actually. Okay. If you have a type 0 system, for omega equals 0 it will start from real axis and it will just travel that way. For type 1 system the plot turns out to be of this nature, and type 2 it will turn out to be that nature. So, knowing this typical building blocks will help us in constructing the Nyquist plot in an intuitive way. I mean some of these things if you know already, then it will be easier actually. Now, remember if you multiply by this gain k, this plot is going to be just amplifying, that means it is like a balloon actually, it will just inflate or shrink actually, it is a function of gain k, okay, because radius r is directly reflected in gain k actually, right. So, if you multiply by gain k, this is going to just inflate or shrink actually. Okay. And these things are very neatly given in Ogata book actually, as we can see, interested you can see. For standard transfer functions you can have the frequency response from Nyquist diagram something like this, the Nyquist plot turns out to be like that. It is nice to remember some of that, because these are nothing but building blocks actually. So, for example, this is a typical second order response, turns out to be like this actually. Okay, omega equal to 0, it starts with somewhere here and then travels, when omega is infinity it converges here actually. Okay, like this. Okay, and similar things are available for many of these things. Like for example, 1 over s if you have, then it just travels in the negative real axis. If you have a simple s in the numerator, it goes in the imaginary axis actually j omega. So, j omega is guaranteed to travel that way. Okay, and 1 by j omega is also like minus j omega. So, it will travel that way actually, that way. So, like that some of these things are handy actually. Now, what is the Nyquist stability criterion? Instead of going into detail, I will directly tell the result, and result is essentially contained in imagining something like, I mean it comes from something like contour mapping theorem in complex number actually, and that is the beauty that Nyquist kind of thought about actually. So, contour mapping theorem details are there in Norman Naish book, some I mean you can read that, but essentially out of all that analysis what it turns out is this beautiful theorem actually. Okay, just read out probably. If a contour that encircles the entire right half plane is mapped through this transfer function GSHS. Remember, this GSHS is nothing but the open loop transfer function, and all the time we are interested in analyzing the open loop transfer function to conclude about the closed loop transfer function zeros, I mean poles actually. Okay. So, if you consider the characteristic equation, that is 1 plus, remember that this transfer function is nothing but T of s equal to k times g of s divided by 1 plus g of s into h of s. Okay. And this, if I just take this denominator and make it equal to 0, that is characteristic equation. Okay. So, if I have some zeros of this characteristic equation, they are nothing but the poles of this transfer function. Okay. But what happens is the fundamental issue is, like if I can study this GSHS very easily, because g of s is known to me, h of s is known to me. So, g of h is GSHS, what is called as open loop transfer function, the poles and zeros are kind of intuitive, obvious actually. So, knowing those details, can I conclude what is happening for the closed loop system? That is the problem, that we saw that in root locus also, same thing actually. So, here we talk about some theorem, this is like this. Okay, we consider the entire right half plane, okay, and then consider how many poles are there in that right half plane, and then kind of imagine a contour around that, okay, contains the entire right half plane, and then this this number of closed loop poles in the right half plane is given by this actually, this expression. That is Z stands for zeros of the characteristic equation, remember that is nothing but poles of the closed loop transfer function. Okay, so, what is it actually? Number of poles in the right half plane minus the number of counterclockwise rotations, this revolution that actually encircles this minus 1 point, and minus 1 comes from this equation again, this 1 plus GHSS equal to 0. So, GHSS is equal to minus 1 actually. Okay, so, that is minus 1 plays a critical role here. So, if I just imagine some contour like that, and then draw this particular contour, I will map it to GHSS plane. This is just simply S plane. In the S plane, I will imagine a contour which contains the entire right half plane, then I will map that to GHSS plane. On the GHSS plane, I will observe two things. I mean, here I will observe one thing, that how many poles are there, open loop poles are there in the right half plane. Here I will observe how many counterclockwise rotations are there around the minus 1 axis actually. Okay. Then I will use this formula and tell, okay, this Z is nothing but P minus N. Okay. And this Z is nothing but zeros of this characteristic equation, and hence it is poles of the closed loop system. That is how it is tied up actually. Okay. So, if this Z happens to be 0, then obviously there are no right half poles of the closed loop, and hence this closed loop system is stable actually. If this Z happens to be positive, that means there is, okay, let us say if it is 1, there is some one pole in the right half plane somewhere for the closed loop transfer function, and hence the system is unstable, like that actually. Example, again if you see that this is a contour that I am imagining first, this is a open loop transfer function, remember H of S is 1, okay. So, that means GHSS is only this what you are looking at, and this contour contains 2 poles in the right half plane actually. So, that count is actually 2, okay. Now, P is 2 here, and if I do this encirclement, okay, actually you can dump this k in the transfer function and talk about encirclement about minus 1, or you keep this k, I mean take out this k, okay, and then encirclement about minus 1 over k, both are same thing actually. Okay. So, what you are looking at, if this particular thing, it happens to be like, if I look at this GHSS plane contour, it encircles this minus 1 over k point twice actually. Okay. So, that n also becomes twice actually. So, P is 2, n is 2, so Z equal to P minus n equal to 0 actually, and that tells me that the system is stable, because the closed loop system is stable, because there is no closed loop poles in the right half plane. That is how the analysis goes actually. Okay. That is the beauty actually. I mean, if you just if you just draw this contour plot, okay, and just do it slightly carefully, then it will do, if you just looking at the number of counterclockwise rotations, remember that this is one rotation, this is second rotation, the counterclockwise rotation will give me the information about stability of the closed loop system. Yes, so it is beautiful in that sense. Also remember, this is a function of k. If k is high, then this point is going to travel more and more close to origin actually. That means, I am more likely to encircle that. So, high gain, if I have a very high gain, that it may lead to instability also. Okay. If I have a low gain, okay, that is a small gain theorem and all that, that will, I mean, this in a nonlinear system also it is roughly true in a way. So, if I have a small gain thing, then what happens, this fellow goes outside of this encirclement, and hence this system remains, I mean, kind of stable actually, but that we will see in a different example also. This example, it just shows that it encircles twice, and hence we have stability actually. Okay. So, this is that another example. The one difficulty comes is, if you have this contour, then on this axis you may encounter singular points also. On the contour you should not have singular points, right. So, infinite poles and all will not be so much worried, but these are the poles, some poles on the imaginary axis, these are points of singularity actually. Okay. So, we should be able to avoid that actually, we should try to avoid that. One way of doing that is put a small circle, small half circle around that, and then interpret that Nyquist float actually. Okay. So, that is done in a detailed things and all, you will find that in Norman Nice and more details in Ogata also. But let us seeing this example, what happens actually, this is a type 1 system, S is there. Okay. So, if you see the type 1 system behavior, something like that should happen. Okay. And that is what is happening for one part of the plane. Remember, these Nyquist plots are always symmetric about real axis in the GH plane also. about the real axis, it will turn out to be symmetric. So, I am able to map that from 0 to infinity sort of thing. Okay, if I infinity, I am starting from somewhere, and if I am traveling something like this, okay, or let me interpret something like that. I start from 0 and go to infinity. Okay, so if I start from 0, I will start from 0 here, okay, then go to infinity, something that way, and then mirror reflection of that. I mean, mirror image will happen that way. It is symmetric about real axis anyway. So, the plot happens to be somewhat like this, and to know this point where it cuts actually, you can see this g of j omega, and that you represent in the real part and complex part, and make the complex the imaginary part, I mean real part and imaginary part, divide it to two parts, and make the imaginary part equal to 0, find an omega where it happens to be 0, and substitute that in the real part to get the value of that. Okay. So, that is how you get a value. Now, this particular value happens to be this particular value happens to be this minus 0.0083 or something like that there actually, okay, which is lot lesser than minus 1. Point is minus 1 is somewhere here, and this point happens to be like that actually. So, what it tells me, like if this analysis tells me that okay, there is no right half poles here, okay, open loop poles, that is 0, and the number of encirclement is also 0 actually. So, 0 minus 0 is also 0. Okay. So, and further analysis tells me that if I work with some gain k which is less than this particular value, then the system will, then the nature will always turn to be stable. Now, remember, if I keep on increasing, then this entire plot is actually ballooning up. That means, it is going to be more and more like a inflation of the balloon actually. So, somewhere at this particular value k equal to 120.5, it will exactly cross through minus 1 actually. Okay, and after that it will become unstable. That is how it happens actually. Okay. So, that is the beauty of this Nyquist diagram, and more details are there in classical control books actually. Now, all this frequency response is well respected even now in industry because of its beautiful concept of robustness actually. Okay. So, let us study that in a slightly careful manner. So, what it is, before you go there, we will just talk about two things here. One is called phase crossover frequency omega, essentially these are corner frequencies sort of thing actually. Okay. Phase crossover frequencies omega Pc, okay, and gain crossover frequencies omega Gc. Okay. These are not really corner frequency, because remember that these phase crossover frequencies are somewhat related to this characteristic equation. We will study that in a little detail here. Okay. They are related to that, but they are not same actually. Okay. So, this is the characteristic equation. Okay. If I plot s equal to j omega, this is the relationship that I am getting actually, right. G of hs or g j omega h j omega has to happen, I mean it should be equal to minus 1 actually, and this minus 1 is nothing but magnitude 1 and angle 180 actually. Okay. So, phase crossover frequency is defined something like this actually. So, it is the frequency at which the phase angle of the transfer function becomes minus 180 degree. Okay. Right, if it is the frequency where the angle becomes minus 180, and the gain crossover frequency is the frequency, okay, at which the magnitude of the open loop transfer function becomes unity actually. Okay. Remember, this g j omega, g j omega h j omega, that is what we are studying here actually. Okay. So, this particular thing contains angle and magnitude. Okay. So, phase crossover frequency is the frequency where this angle becomes minus 180 degree, and gain crossover frequency is the frequency where the magnitude becomes 1, and both are troublesome by the way, because if you have this, then the Nyquist plot will pass through that minus 1 point actually, right. What we are looking at this minus 1 point actually here. Okay. So, this is let us study that in a detail. So, let us say this particular typical Nyquist diagram, let us say we study. Okay. Now, we are happy with that, because this particular point where it crosses the real axis is away from that. So, the difference what you are having here is actually indication of robustness, how much robustness we have. The moment this point travels here, we have a robustness issue there actually. Okay. So, what I am looking at, I am looking at this plot, it turns out that okay, if I multiply this gain by some quantity, it will pass through it, or if I add this phase angle by some quantity, it will cross that actually. Okay. So, as long as I am somewhat like this, minus 1 is outside, I am fine. Okay. All that I want to see is by how much quantity I can multiply this gain, so that this curve will pass through that, or by how much angle I will add this quantity, okay, so that this plot will still go through minus 1. Okay. So, those two values are something like stability margins actually. So, the one is called gain margin, one is called phase margin. So, this the magnitude whatever happens to be, you have to multiply by 1 over kg, right. Suppose this is this magnitude is kg, then 1 by kg if you multiply, then magnitude becomes 1. So, this particular quantity becomes gain margin, and if this angle what you are looking at, that angle becomes phase margin actually. Okay. So, Bode plot, looking at Bode plot, this is the gain crossover frequency, remember that. Okay. Crossover frequency is the frequency where this magnitude becomes 0 actually, right. So, I mean magnitude becomes this log magnitude becomes 0, what I mean actually. Okay. Magnitude becomes 1, so log magnitude becomes 0. So, if you see the 0 line in the Bode plot, then this is the plane, then you go to the phase part of it, then you see how much is there, that is the phase margin. And if you see the gain plot, I mean sorry, the phase plot, there is a phase crossover frequency, and you look back to this gain plot and then tell that is a gain margin that I have. And if this plot happens to be in this way, then both gain margin and phase margins are positive. So, that means my system has some robustness, and if it happens to be other way around, that happens to be negative gain margin actually. So, that means the system is not robust, and but they will happen to be 0 at exactly the same point actually. That curve should pass through -1 point anyway, that will happen to be 0. So, these are the concepts that are much useful there. And then the last concept is something called bandwidth actually, which is also important here. There are further analysis actually, how do you do that, what is called as peak frequency, I mean this closed loop frequency response they are studied little more actually. Then there is a peak frequency, this frequency plot where this curve actually gets a peak value sort of thing. And there is a bandwidth definition, which is actually the frequency range just 3 dB below the 0 line actually. Okay. This entire range I will consider as some sort of a filter idea basically, that any signal will pass through that and all that. And then the bandwidth is defined something like this, omega n into this particular function actually. And interestingly, this function if you plot, it turns out to be like this, that means these are all positive number, and settling time is also like, remember in an approximate sense it is 4 by zeta omega n, that means 4 by zeta by omega n, I can interpret that. That means there is a multiplication term here and there is a multiplication term here actually, that way. So, if you look at these two, settling time is actually inversely proportional to bandwidth. So, if your bandwidth is very high, then the settling time is almost 0 actually. These two you can interpret that as some sort of a scaling factor actually. If I put that together, I can interpret settling time as an inversely proportional to bandwidth actually. Okay. Then that happens to be that way actually. Okay. And another interesting thing is at 0.707, that is our zeta that I am talking about. Okay. Then what happens actually? This zeta value is 0.707. If you see this plot little carefully, this magnitude is 1 actually. That means at that particular zeta equal to 0.7 around that, your bandwidth is nothing but the natural frequency. Okay. So, that is the beauty part of it actually. So, these are all concepts coming from frequency response characteristics, and these are very useful in classical control system design. So, with that I think I will stop here. Okay. There are some points to remember that we have already discussed before, probably I will talk that in the next class also actually.